as we are speaking about the origins and the history, so-called, of deep learning, and more especially the, let's say, breakthroughs that led to its current popularity, we are stopping for a while in some of the things that work much better now in deep learning that they used to in classical artificial intelligence. Work much better is difficult to define, but let's say they are at the very least making life easier for researchers and have had a significant impact in the popularity of the technology. Transfer learning is, again, not a new concept. It was defined many years ago. And from an intuitive point of view, we can say that transfer learning is using knowledge that you have gained from somewhere, solving one problem, first problem, to solve a second problem, another one, solve another problem. So we have an original problem, we solve it, we gain some knowledge from that, and then we want to reuse, to transfer that knowledge to solve a second problem more easily and efficiently than we otherwise could. Okay? In deep learning, usually that means that you train a whole network, you decide all the variables in that large function that we had in the deep learning network mean in order to solve one particular problem. And then once you have done that, you take that result, those weights, and then you start from there when trying to solve a second problem. And I'm going to give some more details in a while. But before of that, I want to say that transfer learning is not something that's alien to us. Humans do some sort of transfer learning, very often referred to as transfer of learning in case of humans, from childhood, and many times, and most of the times without even realizing. And for example, let me just very briefly, it will take exactly 1 minute, read you a poem. And that poem goes: aquesta remor que se sent no és de pluja. Ja fa molt de temps que no plou. S'han eixugat les fonts i la pols s'acumula pels carrers i les cases. Aquesta remor que se sent no és de vent. Han prohibit el vent perquè no s'alci la pols que hi ha per tot i l'aire no esdevingui, diuen, irrespirable. Aquesta remor que se sent no és de paraules. Han prohibit les paraules perquè no posin en perill la fràgil immobilitat de l'aire. Aquesta remor que se sent no és de pensaments. Han estat prohibits perquè no s'engendri la necessitat de parlar i es sobrevingui inevitablement la catàstrofe. I tanmateix, la remor persisteix. So, apologies for those of you who didn't understand a word of that, because that was Catalan poetry by a very famous author called Miquel Martí i Pol. And I hope that you could hear the rhythm, the pitch, and the emotion on the poetry. It's speaking about a noise that's heard, but that noise doesn't come from the rain, because it hasn't rained in a long time, and it's not the wind, and it's not words, because words have been forbidden, and still that noise goes on and on and on. Okay? And my point for reading that was that I learned to read in Catalan and to read poems in Catalan a long time ago when I was a child in school. And I can transfer that ability to English. I never learned to read poetry in English, but I did learn English at some point, and I can try to translate my ability to write Catalan poetry to also reading English poetry. For example, in this one. And don't think it couldn't be you, grievously wounded veteran of the Battle of Bottle, jobless, bereft of home, skinned, down in the cold uriniferous subway, spattered with drool spoil, lying in layers of newspaper ironies, property prices, smoke to the editor's platitudes on the vagrancy issues, ads for Gonzales bias, Dosser in a top man carrier bag and swathed in an FT. Geezer a quid or a 50 for fuck's sake. Bankrupted. I've been fucking well bankrupted. Me. Doland. The whale from the tube. And don't think it couldn't be you. And again, the pronunciation is different. This one is a very nice poem by someone called Peter Redding. But the pitch is the same, the rhythm is modulated similarly, and the emotion, as much as I can do it in English, is transmitted in the same way. In this way, I can use my abilities reading Catalan poetry to try to read English poetry. And in this case, we probably don't need that much new learning. We need to learn some of the different pronunciations in English and in Catalan, but things are more or less close. So this would be probably a good scenario for transfer learning. Perhaps reading from Japanese would be a little bit more difficult because the alphabet is completely different. And for example, here we have a haiku, sorry, I forgot to write it, by Matsuo Basho, that would read Natsuku saya tsuwamono domo ga yume no ato. Very much shorter, in order for me not to butcher too much the Japanese language, as I am already doing that with the English one extensively. But again, here perhaps we have a problem that's a little bit further away from the previous ones, but where we can also apply transfer learning. In deep learning, how is this done? Well, first of all, in order to use transfer learning, we'll need to select one original problem that we'll call source problem or source task. And usually that's selected because of some reason. For example, there is lots of data for that particular problem. And hopefully, the problem that we want to solve and this source problem, this source task, are close. The input data is similar, the output that we want is similar, or the concepts that need to be learned are similar. This is, as you can see, not clearly defined, and this is often a problem in the use of transfer learning. Then, as we said before, we develop a source model. So we solve the source task using perhaps this abundance of data, and we develop the model for the first task. And then we can use transfer learning in different ways. The first one is to just reuse the model. So, for example, maybe I have trained an image recognition deep learning network that can recognize many classes, and now I have new data that's not from the same data set as before, but maybe the classes that I need to recognize, I want to recognize now types of trees, and maybe I'm lucky, and the model that I have trained with another set of data can already recognize these types of trees that I want to recognize, and I can just reuse the model and hope for the best. More often than not, what this means is that I retrain the model. Once I have a model trained, a software that can solve one particular deep learning task, then I retrain it again with my data. And the point is that by using transfer learning, by starting not from a random set of a random configuration of my function, of my deep learning network, but from this configuration that comes after solving this similar problem, then the amount of data that I will need to train my second model will be much less. And this is expressed in deep learning models by often just retraining the last layer of the model. I can train part of it or all of it, or in very common occurrences, just the very last part of my model. And we will get into this in much more detail later. Just to give you a couple of examples of how we have personally used deep learning, transfer learning. These are not particularly, I would say, scientifically groundbreaking results, but they are very familiar to me because I have worked in this and I want to show them as an illustration. So for example, in one paper, we wanted to automatically analyze these WASAN documents, a very interesting historical Japanese form of mathematics. And here at Yamagata University, we have a study program for those. And in order to analyze these documents automatically, we wanted to detect one particular kanji, the ima kanji, the kanji for now, because that's important for the structure of the documents, because it's always very close to this graphical description of the problems. But what happens was that in order to do that, we needed to do several things like correcting scanning angles, cleaning up noise, and finally, what's more interesting for us today, recognizing automatically the kanji characters, the Chinese characters in these documents. But unfortunately for us, these documents are historical. They are from more than 100 years ago. And not 100 years ago, the Edo period, these characters are no longer in use exactly as they are. So it's very difficult to find databases that contain enough examples of these characters to be able to train, to set up, to fine-tune deep learning networks. So what we did instead, one of the things that we tried, was that we did find some classical kanji datasets, and I encourage you to go and have a look at the paper that I will cite in the next slide. But what we did was use modern kanji in their modern writing that's not exactly the same as it was then. For example, here we can see some of the differences. The kanji that we were interested in is written like this today and had a slightly different form then, not super different, but slightly different. Some other kanjis have also changed, and some more than others, as you can see. And what we could do was train with the modern kanji that have lots and lots of databases that are available that we could access with lots and lots of examples. We trained the model with this modern kanji first, and then we tried to fine-tune, to transfer learn from it to a model that had, to a dataset that had the kanji from the period. This is an example of how to use transfer learning in our own research. And we have done more. You have been following our courses, you know that we work a lot with drone image analysis. And for example, there we in one of our papers, that this one I have it here, we very much studied the effects of transfer learning in that one. You can check it, it's available, and available to download for free, it's open access. Basically, we used a satellite image database that had lots and lots and lots of images to train a model first, and then we hoped that that satellite image recognition would be close enough to our drone image analysis problem to recognize these slightly different types of trees. You can see one here, for example. This is a forest of black pine that has an invasive species that's called black locust, and it's not easy to tell apart. And in this problem, we try to use transfer learning to make it easier for us to train the model to recognize these two species of trees using less data, because we didn't have a whole lot of data. You can check the paper. I would say that was pretty successful. Finally, one thing that's very, very often done is doing transfer learning from ImageNet, and you already know everything about ImageNet. It's that huge contest on image recognition with lots and lots of images, lots and lots of different classes. So let's say that the network that is trained with that data set can do things like probably separate objects and identify textures in image. So let's say it's good at the general image recognition tasks. And the common belief is that if you start from there, from a network that had been trained for that particular competition, and then you retrain your model for your images, then that's going to be better than starting your model from scratch, from zero. And that's why in many research papers for image classification, for example, we have a case where we try to recognize three classes of tree health, either sick or dead or healthy, and we try to we do that by starting from a network that was trained with the ImageNet network to recognize, as we were saying the other day, manta ray versus electric ray and these kind of things. But because that network was very good at telling images apart, we hoped, and again the result was pretty good, that retraining that one with our data would provide good results. And this practice of doing transfer learning from ImageNet is very widespread. Not only ImageNet, but other huge databases for other specific problems like object detection or semantic segmentation, and we will also get into that in future videos. Finally, well, almost finally, because there will be lots of things to speak about later, but finally for this video, this has limitations. So for example, when I say I want to find a problem that's close to the problem that I want to solve, but that has lots of data available, that's not rigorously defined, and it's difficult to define what a similar problem is. I remember a good paper where the authors were trying to identify trees and segment, finding the images, the position of tree tops as seen from above, and because those were more or less round, they tried to transfer learn from a data set that had lots of images of balloons that were also round things, and the author thought, okay, so the thing is about segmenting, identifying roundy shapes, so if we train with the data set before, we will get a good solution, and in my opinion they did not. So defining what a similar problem is not simple. Again, it's not easy to know how much data do I need. For some problems, I will need a lot of data even to retrain my network from a network that was trained with something big like ImageNet or so on. Sometimes, on the other hand, if my problem is simple, like identifying something that's very evident in the image, like some invasive species of plants that have a different color from the plants that often live in fields, so that's, let's say, easier to achieve, and in those cases sometimes it's possible to adapt the deep learning networks without needing all that much retraining anyway, so sometimes I don't need transfer learning at all. This brings me to the final point in this video, which is that we are speaking in general about all of these concepts, and I'm trying to give a general intuition. And the beauty of deep learning is that things work pretty well just with these general intuitions. But sometimes that intuition is not enough. These concepts do have some deeper roots and some more complex meanings that sometimes are necessary to achieve the results. And because the area is so popular, most of the research that's done is done from an intuitive point of view, and that's sometimes also dangerous. To sum up, transfer learning works very well, is very often used, but it does have some limitation. It's not a magic bullet.